in the second session, I will talk still something about statistics, but on a very different topic. So I think in the first session we have, discuss a little bit what is the idea behind the Bayesian statistics, right? So adding some prior distributions, and then your prior do have an impact on the final estimation. For example, in the first lecture, the prior distribution is to use to encode the homogeneity, actually the homogeneity and heterogeneity among the different drivers, right? Because you will have some drivers, have a very long trajectory, you will have some drivers have a very short trajectory, and then you cannot do the calibration at the same level of confidence. Maybe some trajectory are too short to provide any meaningful information for you to do the calibration. And then the prior distribution can be used for you to do the proper calibration in the meanwhile, avoid overfitting. And then in this lecture, we can see another application of the prior distribution, which is actually to encode some spatial temporal information into the estimation process. So the second talk I gave is this topic. It's called Bayesian inference of time-varying transit origin-destination matrices from Baldwin and lighting counts. So this is the recent work I had with also two of my PhD students, Xiaoxu Chen and Zhan Hongcheng. So let's get into the motivation part directly. So I think we all come from the transportation engineering background, so we know what does it mean by origin-destination matrix, right? In the transportation planning context, origin-destination matrix refers to how many people are going from origin zone to a destination zone, right? And in the bus operation context, so if I have a bus route with 5 stops from D1 to 1 to 5, the origin-destination matrix of a bus route refers to how many passengers, how many people are going from one stop to another. Okay, for example, here I have 2 passengers going from stop 1 to stop 2. I have 1 passenger going from stop 3 to stop 5, so on and so forth. And for the bus system, is an interesting phenomenon. It's not it's actually a natural phenomenon. Is that for the OD matrix, if I have one direction bus, the lower triangular will always be 0, right? Because I cannot go backwards. I can only go from stop 2 to stop 3. I cannot go from stop 3 to stop 2. So all these entries in the lower triangular part is 0. So OD matrix is a very critical input to transportation to transit operation, because this is actually a critical input for the transit operators to optimize their schedules. For example, how to design the bus route and at what frequency they should do the bus route. And for example, and how do I design the location of the bus stop? It all depends on the OD information. And in the context where I have a mixed bus fleet, so at what frequency I should adopt a different bus, So many of the operation or decision process in the transit operation actually relies on the critical or accurate estimation of the OD matrices. So OD matrix is so important, but how do we collect OD matrices in practice? I think here in Korea, we do have the T-money, right? So in Seoul, we have the T-money system. So when we board the bus, we will type in, right? But when we get off from the bus, do we type out? Yes? Okay, so then we solve the problem, right? So for each of the bus, we will have the type in, we have the type out, and we have all the transaction happens on this bus, then the problem is solved. So because naturally it have the OD matrix, right? And this is the case for many of the Asian countries. In Korea, we have the T-money, and in Singapore, we have the Easy Link, and in many cities in China too, we have the smart card system. So if we have the automatic fare collection system, where we require both typing in and typing off, then the OD matrix is naturally available, accessible to us. But this type of system is only available in a limited number of cities. It's only available, I think, in Seoul or Beijing or Singapore, cities like this, because in this context, these cities normally adopt a distance-based fare. So I have to charge you a certain amount of money based on how much distance you traveled. And then getting the alighting information is very important. But in Montreal, for example, in Quebec, in Montreal, the city I live in, for example, we also have a smart card system. But the system there has a universal fare scheme. As long as you board the bus, you pay $3, no matter where you go. And in that case, the operator does not require passengers to tap off. So if we do not require passengers to tap off, and I still have the smart card data, how do I get the OD matrix? Any idea?
From the videos in vehicle.
Huh?
From the videos in vehicle.
Yeah. Any other solutions?
Fusion with a mobile phone data.
Fusion with mobile phone data. Next best stop, right? So for example, if I use the smart card data, so I tap in from my home and I go to work, but in the evening, this trip happens in the morning, right? But in the evening, I will have a trip from my workplace to my home. So I can probably do some inference for the destination of my first trip, right? So if we follow the trip chain, for example, if I always use public transit, and then I go from A to B, and then if I start a trip B, if I have another trip from B to C, I will probably say, the destination for the first trip is location B, right? So this is the trip chaining assumption. So if I have such a system, I can infer what is the most likely destination for a trip given the boarding location based on the trip chaining assumption. So this is type of actually there's a lot of papers on this topic too, to infer the trip chains based on partially observed smart card data. But what if I use public transit infrequently? I only use public transit once per week, and I only use it one particular trip, and then for the returning trip, I use a taxi or something else. So then, smart card data doesn't help that much, right? But if you look into the population structure, actually a lot of people, in North America, they don't use public transit that often. They are irregular users. But the irregular users may cover like more than 50 or 60% of all the transit usage, and only less than 30 and 40% are the regular users where I can apply this trip chain assumption. And the problem is even more severe in Europe. For example, have you ever been to Zurich, Switzerland? So I think Switzerland has the best public transit system in the world. So in terms of operation and performance, they are very accurate, and all the buses are exactly on time. And in terms of operation, it's the best system in the world. But in terms of data, they are the worst, because they assume that everyone in the city, they have a monthly pass. So they don't even check the ticket. So when you board a bus, you don't have to do anything. And when you get into your destination, you just alert from the bus. So for a city like this, for most of the city in Europe, they actually adopt this system. They don't even verify the ticket, either using smart card or whatever technology. And then for this type of cities, if you want to understand what is the origin destination matrix, what can they do? If I want to collect some data about the origin destination matrices, what can they do? In fact, even for Montreal, getting the origin destination from the smart card data is not an easy task. So the common solution is actually they have to do a trip survey. So for example, in the morning, if I care about the origin destination demand in the morning rush hour, what I do is that I send a person, to the departure location of the bus, and the person will be staying on the bus along the route, and the person will take record of everyone on the bus. Where did this person board the bus at what time, and where did this person alight? When did this person alight from the bus at which location? And once you finish the whole journey along the bus, and then you will get the OD matrix on the bus, on one of the bus. But for transportation planning, for the transit planning, we will need the OD matrices for more than one bus, right? We need the aggregated OD matrix over a few hours, or over the whole morning rush hour period. So to get the accurate OD matrix, either I send a fleet of students, to collect such data, or I do a survey on one bus, but then I do some analysis, I do some interpolation based on the other data set. Actually, the most available data set in these cities is actually the automatic passenger counting data set. And this is the kind of the only available data set for these European cities or North American cities. What it have is that, instead of a smart card system, I have a sensor. It's like a LiDAR sensor, but it could be a video camera too. Deployed inside the bus, and that sensor can, register how many people are boarding the bus and how many people are alighting from the bus when the bus stops at the bus station. And with this type of automatic passenger counting data, what I can get is something like this. So when the bus travels along the bus route, for each of the bus stop, I will see how many people are boarding the bus. So I call it U. So U1, U2, U3, U4. And how many people are alighting from the bus, I call it V. So V1 clearly is 0 because no one will alight from the bus at the departure stop, right? And we only have V2, V3 to Vs. So then the problem becomes, given U1, U2 till Uj, or Us minus 1, and V1, V2 till Vs, how do we recover the origin destination matrix? So this task is actually the OD estimation problem. So is it feasible? Is it possible to get the origin destination matrix from these observations? So if you look at this OD matrix, right? So what is the value of U1? What is the relationship of U2 with this matrix? U2 will be the row sum of this matrix, right? So what is the V3? The column sum of the third column, right? So U2 will be the row sum of the second row, and V3 will be the column sum of the third column. So then, as you can see, the problem is that, are we able to recover the OD matrix based on all these row sum and column sums, right? So naturally, can you think about whether it's possible or not? So for a matrix with like n by n matrix, for the row sum, I will have n numbers, right? For the column sum, I will have n numbers. But how many numbers I have in the OD matrix? If you don't account for the diagonal, it's kind of n minus 1 multiplied by n minus 2 divided by 2, right? So it's almost at the level of n squared. So n squared divided by 2, but it's n squared, right? At that level. So this is the challenging problem. Actually, it's a typical inverse problem because the number of observations we have is at a level of n, at a scale of n. But the number of variables I have is at a number of n squared, right? And our goal is to estimate this n squared variables with those n observations. So OD estimation problem is not only, does not only exist in this context, but in the general urban context, urban transportation is still the same. For example, if I want to estimate origin-destination matrices in the city, but with only the number of cars I counted from the loop detectors on the road, so that will be the same problem, because in the city maybe we have n zones, so the OD matrix will be n by n, right? But maybe I only have n links in the city, so maybe to the maximum I can get maybe 5 times n or 10 times n as a number of link counts. So then how do I recover n squared from 5n? It's the same problem. So let's have a look at the illustration. So for example, these, let's say, so here I use the data set from one city in China, but you can think about it that maybe it's a T-money data from Seoul, right? So this is the real OD matrix on a bus route. So I have a bus route with 20 stops, and entries here shows the real passenger demand registered by the T-money card. Okay, so each entry means the value. But then to illustrate the level of uncertainty, before doing estimation, I have this ground truth matrix, and I will have the row sum and the column sum, and I will have the occupancy profile, like the number of passengers on board the bus at a certain bus stop. So I can apply 3 simple strategies to get this OD matrix. So first strategy, I assume the person get on the bus earlier will get out of the bus earlier. First on, first off. And if I apply this principle, I will get OD matrix like this. And if I apply another principle, last on, first off, which is not that reasonable, but I can still get OD matrix, it's like this. So you can see with this, the same row sum, column sum, I can get a very different estimated result, right? So this is the question, which one is correct? Because both these two are wrong, right? And how do I correctly recover what is in the true OD demand? This is our question to solve. So actually, in Europe and in North America, this is actually a very important problem, and actually there's a big industry behind it. So because doing this type of on-board survey is pretty expensive, because you have to hire a person, and the person has to travel along the bus, and then the person has to do some note. And even that, you are only getting the OD matrix for only one bus, right? So what if in the morning rush hour you have 10 buses? I couldn't really afford the cost to do the survey on all the 10 buses together. So a popular industry practice is that I do the OD survey on one bus, but in the meanwhile, I have the APC data collected from the other 10 buses. So then I could have a meaningful row sum and column sum for the 10 buses together. And from there, I can apply iterative proportional fitting, which is a popular technique I use in population synthesis and OD estimation. I use the collected OD matrix as the seed matrix, and then I iteratively fit the seed matrix according to the marginal row sum and column sums. And then I assume that is my final result. So this is a problem, because even if I apply iterative proportional fitting, in the end I get only one matrix, right? But to what extent that matrix is correct, I have no idea, because if I make different assumptions, I could have substantially different, outcomes. So actually, to solve this problem, we developed some actually I think very useful probability statistical models. So our this talk will be mainly grounded by I think a very big contribution in my opinion, which is this paper from Hazel in 2010. So this paper actually did a very interesting analysis for one bus. So for example, I have the data collected, row sum and column sum collected from one bus, and can we recover that OD matrix? So the assumption in that paper is that instead of using this deterministic method, such as iterative proportional fitting, I can model the whole process in a probabilistic framework. What I can do is that I assume this origin destination matrix can be captured by this lambda. So I assume all these entries are a big lambda vector, and each realization is a Poisson distribution. So this lambda refers to the rate of the Poisson distribution. And then each entry in the OD matrix is a sample come from this Poisson distribution with this rate value. And then if I have the row sum and the column sum, I can write down the likelihood function like this. So you can see, given the rate, what is the probability of observing the row sum and the column sum? So in calculating this, I have to decompose the likelihood function into this. So first of all, it's given the rate, lambda parameter, what is the corresponding value of the OD matrix in the corresponding entry? And then, given the OD matrix, what is the probability I generate row sum and column sum? So this is the correct specification of the likelihood function. But if you look into the calculation of this likelihood, it becomes intractable because in order to calculate the likelihood for lambda, I have to enumerate over all the possible combinations, all the meaningful, or all the potential combinations of the OD matrix. And this becomes impossible because if I have some OD matrix, I can simply do this operation. I pick this entry, I add this entry by 1, I subtract this entry by 1, I subtract this entry by 1 and add this entry by 1. It will be the same, it will be a different OD matrix giving me the same row sum and column sum, right? The row sum and column sum will not be affected by this operation. But how many possible scenarios I have in this case is unlimited. It's actually a very large number because I can potentially generate a very large number of combinations that lead to a meaningful that match the row sum and column sum. So this specification is correct, but as we can see, in calculating it is really impossible because we cannot really enumerate all the possible scenarios. And another assumption made in that paper is that for the lambda values, I can simply assume this type of structure. So for example, lambda ij equals to beta I multiplied by gamma j multiplied by a random term. This is essentially to say, although I have a pretty large number of parameters, but I can assume this parameter is essentially the product of a row vector with a column vector. So that actually limits the complexity of the model. So then I can convert the problem from estimating lambda to estimating beta and gamma. So this assumption, this solution comes from the 2010 paper. But you can see, in general, this model still does not perform very well. Because if you think about the number of parameters, the lambda ij is the set of the OD matrix. So I'm introducing another set of parameters having the same set of lambda ij. And in the case that I don't have strong prior information on this conceit term, the number of parameters will remain the same. And for bus route with many stops, I cannot really do a proper estimation. So the solution actually that paper proposed is to put a gamma, but but a very strong gamma multiplier. So this means that this gamma term is almost a constant value of 1. And then only in this case I can reduce the number of parameters to a row vector and a column vector. But overall, this solution provides us a simple solution that I can do some estimation for one bus. But the problem is that if we see a collection of multiple buses, for example, here I show you a trajectory plot of maybe 100 buses with high frequency service at every 10 minutes. And if I look at the trajectory of these buses, I can see these buses have very different occupancy profile because sometimes you can see in the city we have bus benching happens. So maybe the first bus, you waited at the bus stop for a very long time, but and then you see a bus coming, but this bus is full of people. So it's very crowded. So here I use color to indicate the level of occupancy. If you wait here, you can see the first coming bus has 60 people. But if you, instead of going onto the bus, you wait a little bit, you will see the next coming bus will only have 5 to 10 people on the bus. So in this case, actually, you can see there's a huge variation in the bus. And if I apply this principle into the OD estimation, for example, if I consider I'm doing a survey on this bus, and I use the survey result I get from this bus to extrapolate my OD matrix, pretty much I will get the wrong result because it's not very representative, right? If you use the following bus, I will still get the wrong result because none of them is representative by the overall situation. So then let's think about what else we can leverage in order to get the OD matrices for all these buses over time. Any ideas? So coming back to the assumption, right? So if we follow this framework, the problem is now to estimate what is the lambda for each of the bus, right? What is the Poisson rate for each of the bus? But if I look into the true trajectory data, for example, now let's take these two buses into consideration. One of the bus which looks very full of passengers, and the other bus which is pretty empty. Do you expect the two buses to have a similar Poisson rate parameter? Okay. Because the Poisson rate parameter refers to how many people board from maybe stop 2 to stop 2, and then alight at stop 4, right? But do you expect this number to be the same for these two buses? We cannot expect that, right? If the trajectory is all uniform, all parallel, then it could be okay. Because then the service is homogeneous and then all the bus runs identically, right? But in the real world scenario, for the first bus, I will see a lot of people boarding, right? At any of the stops here. And for the second bus, I will see essentially there's no one boarding the bus, right? If you look at the Poisson rate, essentially I cannot assume these two buses are the same, right? But is there anything we can leverage? I know these two buses have very different lambda. The lambda is very different. But is there anything remains similar or remains the same for the two buses? The one thing we can assume remains the same is that, so actually there are two ways to think about this lambda. So the first way is that I have this lambda Poisson rate, right? But the second thought, second interpretation for this lambda is that I can assume there's overall, boarding rate at this stop 1, but then I assign these passengers to different stops using a multinomial distribution. Multinomial distribution is like you draw the ball, right? Red color, blue color, and then black color. You assign this, into different jars. So if we follow this second interpretation, and then I decompose this lambda into two parts, I have an overall lambda, and then I have this multinomial distribution. Can I assume the multinomial distribution is the same for the two buses? This assumption makes sense, right? Because no matter for those passengers who are waiting at this bus stop, no matter which bus you get into, you always have the same probability to go to the following destination, right? But the lambda rate could be substantially different, but then the multinomial probability almost looks like the same, right? So this actually, the whole idea about this work. So a very important prior knowledge is that we can actually expect a lighting probability. So instead of using the lambda rate, I can expect the lighting probability to vary, but it should be very, very smoothly over time. For 2 buses, 3 buses, I can almost expect they have to be the same. But if you think about the buses operated in the morning rush hour and in the evening rush hour, they should be substantially different, right? Because in the morning rush hour, I go from home to work. And the evening, people are going from maybe CBD to home. So the probability is very different in the morning and the evening. But in the morning, the probability for different buses, we can assume is almost the same. And then with this prior knowledge, we can build our model. So our solution is that instead of modeling this lambda, we model this probability. And I assume that for this collection of buses, so for example here I have 1, 2, 3, 4, 5, 6, 7. So I have 8 buses. So for each of the bus, I will have this matrix as a parameter to be estimated, right? But if I combine these 8 buses together, I stack all of them. First of all, I convert this matrix to be a single vector. And then I stack these vectors together as a matrix. So this matrix will be having the size of n squared, half of n squared multiplied by 8. So they assume there's 8 buses. And for these 8 buses, because we know it is operated over in the same hour, probably from 8 to 9, and I can assume, in terms of probability, they always have similar probability, right, in terms of going to which destination. So the solution we propose is actually to replace the Poisson likelihood with the multinomial likelihood, and in the meanwhile, we convert the problem to from estimating an upper triangular matrix to the estimation of a matrix. So it seems that we are doing nothing here because it's still the same number of parameters. But why am I modeling it into a matrix? What is the advantage I can get from modeling it as a matrix? So in fact, this type of parameterization gives us a lot of opportunities, because if you think about this matrix, it has the same number of parameters as the original case, but for a matrix, if I see a very big matrix with so many entries, to simplify the matrix, actually the first thought I have is actually to apply something like PCA, right? Principal component analysis or matrix factorization. Because that is the the primary technique we can leverage for dimensionality reduction. For this big matrix, maybe I can apply dimensionality reduction to factorize it into two smaller matrices. So I will have one matrix on the OD demand dimension, and I will have another matrix on the time dimension, right? Or the vehicle dimension. And that is the idea how we parameterize this matrix. So first of all, so we can convert the problem to parameterizing this, each of these column. The blue color column with the multinomial distribution, the green color column with the multinomial distribution. Each of them is a multinomial distribution. And then stacking them together, we get a matrix. And to parameterize the multinomial distribution, we have essentially in machine learning or statistics, we have two choices. Either using a derivative distribution, or in machine learning, a popular choice is using softmax parameterization, the softmax function. And here, to make it things easy, we can use the softmax function here. And to reduce the dimensionality of the problem, so what we suggest is we can do matrix factorization. Because we know all the 8 buses should looks very similar, right? So then they can be decomposed into two smaller matrices. Especially on the temporal factor, because I should expect the first bus should be very similar to the second bus, right? But how about the first bus to the 8th bus, to the last bus? They should be not that similar, right? So the first and second should be highly correlated, second and third should be highly correlated, but there should be probably a small correlation or even no correlation between number 1 and number 10, right? So is there any way we can do this kind of parameterization? I think this reminds us, what we have learned from the first lecture, right? So the technique we use in the first lecture is the Gaussian process. Gaussian process can capture, correlation structure. And then it can capture, the length scale can introduce how much local correlation I have. And once we go beyond the length scale, it becomes independent, right? So the whole same idea here, I can use a Gaussian process to capture what is the temporal correlation in the temporal matrix. And this is actually the whole idea behind the model. So we propose the multinomial likelihood construction. And then we propose to parameterize the big matrix into using matrix factorization. And then one additional proposal is that for the temporal factor, we can use Gaussian process to parameterize each row actually of this matrix. And then come to the inference part. The inference part is a little bit difficult, but I will mostly skip most of the part. But the inference actually requires us to do Markov chain Monte Carlo. So we have to do an iterative-based procedure. Every time I have to sample what is the parameter in the model, and then I sample what is the potential latent observation of the vector. But I will not go into talk about too much details about how to do MCMC, because MCMC is essentially the technique we use for Bayesian inference. But the procedure is like this. We can first sample what is the latent OD vector from this distribution. And then I can sample the decomposed multinomial matrix one by one. And then I can sample this kind of temperature parameter we defined there. But after a large number of MC Markov chain Monte Carlo iterations, I can approximate what is the posterior distribution of the OD vectors. So now let's get into the experiment part. So we did some analysis on 3 example bus routes. So one short, one medium, and one long. So with 22, 40, and 72 bus stops respectively. And we have the ground truth available because we do have the T-money data, for this 3 bus stop. But we are not going to use it. So the goal is actually to recover the OD matrix from only the row sum and column sum without using the true observation. So we can see there are 3, so these are the examples of the 3 bus routes with the boarding flow, lighting flow, and then one of the bus routes. For the short bus route, we have the boarding flow, lighting flow, and then OD flow. So the goal is to use only these 2 matrices to recover the third matrix. So let's get into the analysis part. So for the MCMC, we run the algorithm for 10,000 iterations, and then because it's pretty slow, so we take the first 95,000 that burn in. We, during the convergence process, we actually discard this part and only use the last 5,000 iterations to do the posterior approximation. So here is our result. So first of all, let's see the estimated result. So in order to do a proper benchmark, so we compared our model with the simple solution of iterative proportional fitting. So these are the results. So the x-axis is the true OD demand in the matrix in each of the bus and each of the OD type. And the y-axis is estimated value from our model and also the IPS. And here we have 3 figures showing the 3 bus routes. So first of all, as you can see, the blue model, which is the iterative proportional fitting model, doesn't perform very well because we can see there's a big problem in IPF because IPF only take 1 bus as a seed, right? If the seed matrix is incorrect or not its best, so whatever you can get from the seed matrix will be almost incorrect or best. Also, the seed matrix in the iterative proportional fitting method, there's a lot of structure 0. So if you have 0 in the seed matrix, no matter how many times you do the iterative proportional fitting, it will remain 0 all the time. So it has a structure 0 problem which cannot be easily solved. But on the contrary, if we look at the model, the result estimated from this new model, you can see the result along actually scattered along this 45-degree line pretty well. And another way to verify the result is actually to see what is the structure of the temporal factor. And for simple realization, we can plot what is the Markov chain, the obtained samples from the Markov chain Monte Carlo for the temporal factors. So here I showed the result with a decomposition with rank equals to 4. So we have a large matrix. The large matrix is probably 400 by 500. So 400 OD entries, 500 buses. But then what we suggest is that we can decompose this large matrix with a rank 4 decomposition, which means the 2 smaller matrices only have 4 columns. And with that, I can visualize what is the temporal matrix. And you can see with this strategy, with this new model, the estimated temporal vector actually looks pretty good, and it can also encode the temporal periodic structure. So this is not specified in the very beginning. So we didn't specify this, but the posterior result tells you, you can see the pink colored cluster. It almost repeats itself from Monday to Friday, right? It means that from Monday to Friday, it almost the temporal factor almost remains the same. And this is one of the realization about the lambda 1, which is a lighting probability. So how this probability varies over the day. So for example, from morning to the evening, I have 100 buses, but for each of the bus, I will have a probability distribution. And you can see
the estimated probability also have this kind of daily periodicity, right? So it's pretty clear, from morning to the evening, there's a time varying structure. So the next property about this inference is that the result is that we can do this, right? So this equation, if you look into this equation, we can do posterior inference. Not only the parameters, we not only get the posterior distribution for these parameters, but we can also get the posterior distribution for each of the entry in the OD matrix. So if we look at that, we can get some interesting result about what is the estimated OD matrix for each of the bus, for each of the cells. So here I give you an example of the 4 cells in the OD matrix, and the blue dots shows the true value, and then the red area covers, shows a 95% coverage or the interval of the distribution. So I can see this is for the short route. You can see the blue dots are well covered by the red area, and the red area is not so large, right? So everything is well covered. So in summary, this is another work I introduced about how to use statistical modeling to solve transportation problems. And this is a very classical transportation problem about OD inference. And similar to the first lecture we did for the Calibrating model, we introduced the prior over the population, right? But in this case, we introduced a prior, for the parameters. And we introduced actually 2 types of priors to simplify the model. So one prior is, for the temporal factor, we use Gaussian process, right? So we expect the nearby buses to be similar, to have the same parameter. But the other prior is actually the parameterization, the matrix factorization itself, because this is actually a low rank prior. Because you have a large matrix to be estimated, but I have very strong belief that this matrix, although it looks very large, but it's inherently, it only is very structured. And I assume it can be factorized using a matrix factorization model with a very small rank, rank 2 to rank 5. And we can see a small rank of 4 can actually well reproduce the OD matrix we have. So with that, I showed you how we solved the problem, and we can see this Bayesian framework is pretty powerful in actually not only estimating the parameters, because Bayesian also allows you to do this kind of posterior analysis. So this equation, it essentially tells you Bayesian can allow us to do an integration over the models, because what happens in the in the modern machine learning is that I have a data set, right? And then what I do next is that from the data set, I get a set of parameters, which is the trained model. And from the trained model, I can get my prediction, right? But in the Bayesian context, the model is not important, because I assume the model itself is a random variable. So what the Bayesian tells you is that based on the observe the data itself, I can directly approximate the posterior distribution for anything I want to predict or anything I want to estimate. And the idea of achieving this is through the Bayes equation. I can integrate over all the potential models. So why we are integrating all the potential models here? Because how did we achieve that? Is that you can see here, I mentioned that I run the Markov chain Monte Carlo for 10,000 iterations, right? And I leave the last 5,000 iterations to do the analysis. So what we can think is that each of these 5,000 iterations is a model. So overall, we have 5,000 models. And if we do the integration over the 5,000 models, I actually have everything here. So it's kind of integrating all these 5,000 models. So this scheme also allows us to achieve optimization and uncertainty quantification. So not only the probability, but also the prediction. I can get not only the mean, but also the potential distribution. So with that, I finished the second lecture. Everything I have is here. And the paper, if you are interested, is actually available online. You can have a look. So that's all. Thank you. So probably we have some time for questions.
Okay, can I just ask one question? Because in the social sciences we use Bayesian as well, but then our iteration number is around 1,000. So is there a reason why you chose the iteration to be that large, or is that like kind of the norm in the transportation engineering?
That's a good question. So it's not necessary. Actually, we just choose this number. We can do the analysis with 1,002, and I think the result will be almost the same.
Okay.
Yeah. But here, I think one problem I think one reason we choose 5,000 is that the autocorrelation could be a little bit stronger in the compared with the conjugate case, because in the inference we have a large set of latent variable which is unknown, and we have to sample it. So in doing this, compared to the conjugate case, we will naturally introduce a long-range correlation in the Markov chain Monte Carlo. So that is to say the convergence is a little bit slower than a general Bayesian model. And if we want to estimate the posterior, so the solution to address this autocorrelation is that I have to run the iterations much longer, and then in the final approximation I take like one sample every maybe 10 or 20 iterations. So that is why we use 5,000, because we try to avoid this autocorrelation, strong autocorrelation in the results. Yes.
Thank you for your presentation. So I think using a temporal tendency, we can complement the inference morning pattern with by using a night pattern, because as you said, people in the morning people go to work and they return home in the evening. So we can inverse the nighttime pattern. So then we can complement the morning pattern.
Yeah,
So
I think that's a very interesting proposal. So actually, here all the analysis is based on one bus route, right? But it's only for one direction. But we know bus route runs parallel directions, right? You have one bus route from A to B, and then you have another bus route from B to A, and it's actually carry the same group of passengers, right? So maybe this is something we can leverage too. If I have two bus routes, and maybe combining these two bus routes, I can have a better distribution, because then the temporal distribution will give you factors. For example, for which OD pair on this two bus route are going for the morning commuting people, right? And for which OD pair they are for the evening commuting people. So it's possible actually.
Any other questions? All right. I guess it's the last lecture they want to leave off.
Yes, I think we're tired. I'm tired too.
All right, thank you very much.